Hello there, welcome to another video of computer organization and system. In this particular video we are going to have an introduction on combinational circuits. So let's start with that. So a combinational circuit is a connected arrangement of logic gates with a set of inputs and outputs. So the point which is to mention is the logic gates which are having certain inputs and certain outputs. A combinational circuit transforms the binary information from a given input data to the required output data. So that means we are talking about certain kind of logic operation which is supposed to be performed on that particular input set. Apart from that, a combinational circuit are employed in digital computer for generating binary control decisions, right? And for providing digital components required for data processing. So two major responsibilities of combinational circuit is that providing the control decision things, and apart from that, processing of the data, right? So as we said circuit, so that means there will be n number of combinational circuits which exist in a digital computer to perform various kinds of control decision operations and the data processing on them, right? So one thing which I wanted to mention here is that there is no feedback mechanism with this particular combinational circuits is available, right? So that is for the sequential circuits, which we are going to discuss in another video, but there is no feedback which exists for the combinational circuit, which we always need to mention, which we always need to keep in mind. Now when we wanted to design any kind of combinational circuit, that particular combinational circuit is always designed for a specific problem, right? So we are actually going to follow certain set of steps for generating the combinational circuit. So there are basically 5 steps which we do. The very first step is the problem statement. We actually find out that what exactly we wanted to automate through the digital computer part, and then we start designing the combination circuit corresponding to it. But the specification is very important that we need to take care of. Now once we have a specification, then we actually identify that what are the input and outputs, and then we assign certain variable symbols, letter symbols to them. Then by identifying that what operation we are looking for and what relationship is there between the input and output, we try to devise a truth table, which is one of the very important activity which we need to follow. Once we identify the truth table, it's very easy to find out the patterns and then devise the Boolean function as well as the logic diagram corresponding to it. Now when we have a truth table ready, we can actually specify a Boolean function corresponding to it, and then we can actually go and design the logical diagram, right? So when we are saying the logic diagrams and so on, so Boolean functions are generally corresponding to certain kind of logic gate, combination of logic gates which we are supposed to use, right? So the truth table plus Boolean function are actually going to tell us that what set of logic gates we are going to use corresponding to it, right? And once we have that, we create a logic diagram with that particular combination. So let's take an example of addition operation. So if I am doing a decimal addition, and I have two numbers to solve, that is 25 and 36. In this particular case, I have two expressions to solve, that is 5 plus 6. Now 5 plus 6 is equals to 11, but as per the rules of the mathematics, I cannot write 11 here. One of the digit is going to be on the sum and another digit is going to be as a carry, right? So this part is sum and this part is carry. So that means the second expression which I am going to solve right now is 1 plus 2 plus 3, that becomes 6. So this is what we have. In binary also the similar kind of pattern is followed, right? So we work on the sum part, we work on the carry part too. So let's say if I talk about two inputs A and B, both are having certain value on them. So the value which they can both of these inputs can have either 0 or 1. So let's say if I have to add a value A which is 0 and value B which is 0, the outcome which I'm going to get is 0, right? So what I'm doing is I'm doing 2-bit operation here, where 1 bit belongs to first input and second bit belongs to the second input, right? Similarly, if my A is equals to 1 and my B is equals to 0, in this particular case, my output will be 1, right? What if I have A as 0 and B as 1? My output will be 1 in this case. Now, what if I have A is equals to 1 and B is also equals to 1? Then my output here is actually, when if you remember the addition operation on the binary part, 1 plus 1 is 1 0, right? So 0 will be actually a sum here, 1 will be given as a carry because there is no certain bit position which is available, because the data is actually a 1-bit data, right? So C is actually kept as a carry, right? So if I wanted to write it here, it will be kept as a carry but will not be represented as a part of the particular output, right? So this becomes 2-bit for me. Okay, so the sum is kept separate and carry is kept separate. So a lot of things we are going to study further, where this carry is maintained and then later on added to the the complete expression and so on, right? So till this particular place, what we can do is we can save the sum at the different place and save the carry at the different place, but the final outcome which I'm going to get for 1 plus 1 is 1 0, right? So this one is catering this particular thing is very easy, because right now no carry has been generated further to this level. But what if I have an expression, or maybe another expression here? So let's say my A is a 2-bit number, that is 1 1, and my B is a 2-bit number, that is 1 and 1, but at one point of time only 1 bit can be solved. So when first bit was solved and the outcome will be like this, in that particular case my carry is going to be generated for the next value, right? So in this particular case I need to take care of this previous carry and then I have to add it. So when we are doing a addition operation for these kind of bits, so 1 plus 1 plus 1 is actually equals to 1 and 1. How this happens is, because when I do 1 plus 1, in this particular case I'm going to get 10, right? And this sum part is separate, okay, this carry part is separate again, so the another one is actually going to be added to the sum part, and this gives you 1 and 1, right? So I hope you understood from this. So these are some of the cases which we need to take care of. So let's start with the 1-bit addition, where A and B are both 1 bits. So in this particular case, we have, as we have gone through this particular text, we know that they can have a combination of 0 0 0 1 1 0 and 1 1. So the outcome which I am going to get here is for 0 plus 0 it's 0, for 0 plus 1 it's 1, for 1 plus 0 it is going to be 1, and from 1 plus 1 it is going to be 1 0, right? So in this particular case, if I try to figure it out, if I try to segregate it into two different parts, that is sum and carry, A and B. So I'm writing the same thing again, 0 and 0, 0 and 1, 1 and 0, and 1 and 1. So in this particular case, if I'm adding 0 and 0, the sum will be 0 and carry will also be 0. If I'm adding 1 and 0, the sum will be 1 and carry will be 0 again. If I'm adding 1 to 0, then sum will be 1 and carry will be 0. Whereas if I'm adding 1 and 1, the sum will be 0 but the carry will be 1. So we are maintaining two different sets here for performing the addition operation on these two inputs, right? That is A and B. So this set is input, this set is output. So if you try to figure out that what is the pattern which is happening for C and S, carry and sum. So if I go with this particular carries, so if I give you an AND truth table, if I have two inputs A and B, 0 0 0 1 1 0 1 1, the property of AND output, the AND operation is that when both the inputs are high, only then the output is going to be high. So that means 0 0 0 and 1. So if I try to match C with AND, it's totally perfect. So that means this particular operation can be resembled by using AND logic gate. Now let's look at the S. It says 0 1 1 0. So if I give you a gist of XOR truth table, it says if I have two inputs A and B, 0 0 0 1 1 0 and 1 1. So if I go with the output of the XOR, so what we are going to have is when both the inputs are same, the output will be 0. When both the inputs are opposite, then the output will be 1. So this is what we get the XOR. So that means S can be represented with the XOR logic gate, right? So this is what we have. So that means if I wanted to represent this particular set of truth table as a circuit of 1 bit value from 2 inputs, then it can be designed as we mentioned, that we have XOR, which is representing S, and we have AND, which is representing carry. So the expression which will be A bar B plus A B bar, whereas for carry the expression will be A multiplied by B. So the circuit which is going to be there is, we have a XOR gate with we have a XOR gate which is producing S, we have an AND gate which is producing C, we have 2 inputs A and B, right, which are given to the XOR, and the same set of inputs are given to AND operation, right? So this is what becomes a 1 bit adder operation. So we also call it half adder because it is not taking care of the previous carry, right? We are not taking care of the previous carry here, right? That is the case of 1 plus 1 plus 1, that gives me 1 and 1, right? So we have to take care of that particular thing too. So for that, if we wanted to have the previous carry and so on, so we have to create a truth table corresponding to it. So we have A, B and carry, right? And our corresponding outputs are C and S. Obviously this is carry and this is sum. So we have values like 0, 0, 0, 1, 1, 0 and 0, 1 and 1. So we say that there is no previous carry, then the output will be similar, that is carry 0, sum is also 0, 0, then carry 0 again, sum is 1, carry 0 again, sum is 1, and carry 1 and sum is 0. Now next thing which comes is that for 0 and 0, if my carry is 1, then in that case what I'm going to get is 0 carry, but sum will be 1. If I have 0 and 1 given for both the inputs and 1 carry is also given, then in that particular case what we are going to get is 1 and 0. Then if I say that my A is 1 and B is 0 and carry is also given as 1, in that particular case again I'm going to get a value 1, 0. What if my input A and input B both are 1 and my carry is also 1? In that particular case my output will be like this. Now if you see carefully, what we are going to get here is that this particular set is all half adder, right? And this particular set is a bit different in terms of, because we are having a previous carry, right? So if you try to consider that when both the inputs are 0 and the carry is 1, the output is actually equals to this particular set. So these two values outcomes are same. Similarly, if you see if there is at least one input is 1 and the carry is there, then these two outputs of the second part is actually equivalent to this, right? That is the fourth output of the first half adder. And the only case where we differ is actually in this particular part, that is when we have both the input is high and carry input is also high. So we have to have a carry as well as some places also 1. So both are equals to 1. So this one is different. So what we can actually do here is that we know that till this particular place we can have a 2-bit addition in terms of one bit from A and 1 bit from B, right? A and B. So we can do a addition on them, and then we are talking about the third bit. So that means what I can treat is that output from this particular 2 bits right, can be added to the another 1 bit of the carry, right? So that means we can actually go and utilize the 2 half adders in this particular contest, and to maintain the carry part, because we also need to take care of this particular case, to maintain the carry part we can use a OR gate at the end, right? So let's see how it is going to happen. So as we already know that this particular half adder requires 2 inputs, right? Like we have displayed here, this is a kind of clean logical diagram. So we have a XOR here, single XOR, and we have a AND, right? So when for this particular part we can easily do a 1 bit addition. 1 bit addition of what level? That is only one single bit is available. We have a sum and we have a carry. What if I have a number A equals to 101 and number B equals to 101? In this particular case I need to do the addition, as I mentioned in the previous slide here, that we can have 2 half adders, right? So in this particular case what I have to do is I have to actually put combinations of certain half adders into the pictures, right? So till this particular place half adder is worked out, but we have to go for the full adder, right? So full adder will be like this, in this particular way. So if you see carefully, this particular part and this particular part, I would say I must create a separation for you. This and this, these are 2 half adders, half adder 1, half adder 2. They have been joined together, and if you see, the carries are being actually OR operation is performed on the carry, right? So finally we have to maintain the carry 2, right? So in this way, two different half adders can be joined together to produce a full adder operations. Now here what we are able to do is we are actually able to cater this particular case, that is if 2 inputs are given and the carry is also given, that can be taken care of, right? So let me solve an expression for you. So we have, as I have mentioned in the previous slide, that is A is equals to 101 and B equals to 101, right? So if I wanted to solve this particular expression, I actually need to go through 3 clock pulses, right? So 3 clock pulses means I am going to give these inputs at 3 different in 3 different intervals. So we have expression here for full adder, because we are doing 2 XOR operations and we are doing 1 XOR operation in carry. This can be taken care of. So here let's start with the first least significant bit. So we give 1 and 1, and right now if you see, carry I will be doing side by side. So right now the carry is 0, no carry is there from the previous bit, so we have 1 1 0. So when we do XOR operation, so both the inputs are high, the output will be low here. Whereas when we go with the AND gate, the first AND gate, right, AND gate 1, AND gate 2, XOR, let me give them numbers, XOR 1 and XOR 2. So XOR 1 is producing low, but AND, because both the inputs are high, so AND 1 will be producing high, right? So in this particular case, the first level is completed for the half adder. Now I need to solve the second half adder level. Now here XOR is 0 at the first input and Cin is also 0, right? So output will be 0 here, right? And if I go to the next AND, so both the inputs are 0, the output will be 0. The Cout will be now, because this is an OR operation, so 0 and 0 becomes 1. So if you see carefully, so what I'm going to get is, in this particular case, 101 101, we have a 0, but we have a carry, right? We have a 0 and we have a carry. So let me do it in a similar way. So let me rewrite this particular expression. So we have C, we have A, and when we have B, and the output is like this. So what we have is 101 101, carry is 0 at this particular place, sorry, 101. So the first values has been solved. So what we are going to get is, here I'm going to write S. So 0, but for next particular cycle the carry will be actually connected with this, right? So this is what we are going to have in this particular case. The carry is going to be fed to the circuit for the next cycle. So here if you see the values right now for A and B becomes what? This becomes 0, right? So that means 0 and 0. So when both the inputs to XOR 1 are 0, the output will be 0, but my carry right now is 1, right? So once the first AND gate 1 gets the two inputs 0 and 0, this becomes 0, right? Whereas now Cin is 0, Cin is 1 and XOR 1 is having the output 0. So this part 0 and 1, this becomes 1. XOR 2 is now going to give me output 1, whereas on this particular AND gate 2 the value for carry in was 1 and second input that is given from the XOR 1 output to the AND, that becomes 1. So 0 and 0 gives me output as 0. So my output here will be 0, but my sum is 1. So I'm taking care of 1 0 1. So if you see my truth table where both the inputs are 0 but carry from the previous input is there, right? So let's come back to the circuit again. So next that we are going to get is both the inputs are 1 and carry is 0 in this particular case. So let me clear this. So previous carry which we got is 0, so that means C in 0, A is 1, B is 1. So both the inputs are 1, or high on the XOR 1, so it is going to give me 0. C, and for AND gate, because both the inputs are 1, the output will be high in that, and in the second set of half adders. So C in is 0, so when both the inputs to XOR gate is 0, it becomes 0, right? And for AND gate again it's 0 and 0, the output will be 0, and once you give any of the high value to the input to of OR gate, it becomes 1, right? So in this particular case the sum is 0 but the carry has been generated 1, because now there is no another bit which is supposed to be added for input A and B, so we get the carry as 1. So final outcome will be like this. So if I convert this A and B 5 and 5, the output must be 10. So if you convert this 1010, this is again a value, decimal value 10, right? So this is how the addition operation is taken care of by using the full adder in actual digital computer system. So that means what we have is in the real digital computers. So let's say I wanted to add 4 bits, right, and where the addition is to be done for 2 numbers, right? So each number is of what, 4 bit. So in that case what I'm going to put is full adder 1, full adder 2, full adder 3 and full adder 4, right? So we have full adders, 4 full adder circuits here. Each full adder will have 2 inputs, right? So A0, B0, A1, B1, A2, B2, A3, A4. It will produce me sum 0, sum 1, sum 2, sum 3, and there will be a carry which will be fed to the next full adder, that is C0, C1, C2 and C3 will be a output carry, right? So in this way we actually put a combination of full adders for each bit so that it can cater the previous carry too, and here also the carry in is given if there is some other circuit in the picture, right? So this is how overall the addition operation is done for a particular digital computer by using a combinational circuit. Now nowhere here you will find a storage element, right? which is actually a flip-flop. We are going to discuss it in next particular video, but there is nowhere we have storage. So what you do is you take the input, right, and you throw the output to the system, or maybe you fed it to the next particular combinational circuit, as we done in this particular example. So the carry is fed into the next circuit from each previous circuit, full adder circuit, right? So this is how the combinational circuit works out for your digital computer to process the data. And on the similar pattern, there are certain control circuits which are being used for doing a control decisions, right? So this is how the whole thing works out. So you actually use a logic gate at the end, and the various combination of logic gates, and then you produce the things. And how you design, this is how you actually need to figure out that what pattern is matched with what particular gate and what can be put into the picture, right? So I hope this particular video had made some clarity on the combinational circuits of digital computer, and with that I just sign off. Thank you very much for watching, and please do help us to improve us on preparing such kind of videos. Please share your comments and feedbacks in comment section below. Thanks very much for watching, and keep tuned for the next video. Bye bye.